Today we're going to practice the radicals practice number 2, which is simplifying, rationalizing, and conjugates. So let's go ahead and get started. So we're going to combine 3 square root of 5 minus 2 square root of 5. The thing about adding and subtracting radicals is you have to look underneath the square root, or the root value. So looking underneath, I have the square root of 5 and the square root of 5. These are like terms, meaning I can just focus on the values that are in front. So basically, since these are identical, I'm going to just do 3 minus 2. 3 minus 2 is, 3 minus 2 is 1 square root of 5. I was looking at my answer key. I, for some reason, wrote 5 because I'm silly. So I was like, that's not right. And we also don't have to write the value in front, so we can just leave that as square root 5. Let's try the next one. So in the next one, again, the square roots are the same. So I can just add the coefficients, 5 plus 2. 5 plus 2 is 7 square roots of 6. For the last one, we have square root of 5 and square root of 5. So again, adding the coefficients. 8 plus 10 is 18 square roots of 5. You don't go underneath the square root unless you're multiplying, so we just need to be careful. All right, next problem. 8 square roots of 2 plus 12 square roots of 8. So looking at this problem, I see that 8 has a perfect square in it. That perfect square is 4, so 4 times 2. Remember, you can use that little perfect square chart, or you can use a factor tree with groups of 2. So I know that 8 divided by 4 is 2, so 4 and 2 are my factors. When I square root the 4 and the 2, this 8 square roots of 2 just kind of follows along, nothing interesting, as well as the 12. The 12 is still a part of the problem. So the square root of 4 is 2 square roots of 2. Now we have identical values, so continuing to simplify, I have 8 square roots of 2 plus 12 times 2 is 24 square roots of 2. And now I can go ahead and add. So 8, just like we did before, 8 plus 24, since the square roots of 2 are identical. 8 plus 24 is 32 square roots of 2. Looking at the next problem, I see a 75. Well, I should know that the 25 is the perfect square that goes into 75. And 75 divided by 25 is 3. So I'm going to square root those. The square root of 25 is 5. The square root of 3 is stuck underneath. Can't do anything with it. I'm going to bring down the square root, the 3 square root of 3. I'm going to look and see, okay, these square roots are identical, so I can add 5 plus 3. So 5 plus 3 is 8 square roots of 3. And the very last one, I see 48, so I know that 16 goes into 48 3 times. As I simplify this, I'm going to bring down that 2. The square root of 16 is 4, and the square root of 3 cannot be simplified. Bringing down that square root 3. Now I'm going to distribute. I have the 2 times 4, which is 8 square roots of 3 minus the square root of 3. Well, 8 minus the square root of 3, there's really kind of a 1 right here. So 8 minus 1 is 7 square roots of 3. So when you're adding and subtracting square root values, you want to make sure that the square roots are identical or they can be simplified. So always being aware of perfect squares is going to make this a lot easier. Down here, we're going to do rationalizing. So right here on number 8, we need to put a square root sign over 5. That is completely my fault. I forgot to do that when I was copying. So let's rationalize. So when we rationalize fractions, basically what we're doing is just changing their appearance, meaning we don't like the way that they look. We can't have a square root in the bottom. It's not proper. So what we're going to do from here is we're going to go ahead and actually move the square root by multiplying the top and the bottom by the square root. Not the number in front, only the square root. This fraction is technically just 1, so we're not actually changing the numeric value. We're just changing the appearance of the fraction. So now I can multiply across. 5 times the square root of 3 is 5 square roots of 3. Then underneath, this is where our multiplication comes in. We're just going to bring down this 2. And then we're going to do square root of 3 times the square root of 3, which is the square root of 9. And the square root of 9 is 3. Now we're going to multiply them because we're multiplying them up here. So 2 times 3 is 6, which is the value that goes on the bottom. We can't simplify this fraction right here, so we know that we're good. All right, trying the next problem. In the denominator, I have the square root of 5, so I'm going to multiply the top and the bottom of this fraction, square root of 5. Again, this fraction is just a 1. We're just changing the appearance. So let's go ahead and multiply. So 2 times, remember there's like a 1 out here. 2 times 1 is 2. The square root of 3 times the square root of 5 is the square root of 15. To get the denominator, I do the square root of 5 times the square root of 5, which is the square root of 25, and the square root of 25 is 5. Looking at the top and bottom, I notice that 2 and 5 can't simplify, and I can't pull a perfect square out of 15, so this problem is complete. Number 9 is another rationalizing question. It's not a conjugate because this plus piece is in the top, not in the bottom. So we're just going to multiply by the denominator. It is going to take a little bit more work because we do have that plus sign, but it's nothing that you can't handle. It's nothing that is more difficult. It's just a little extra step. So to multiply, I have 2 times the square root of 3 for 2 square roots of 3. Then I shift over here. The square root of 7 times the square root of 3 is the square root of 21. 7 times 3 is 21. For the underneath part, I bring down the 6. Then I multiply. The square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is 3. I multiply these two terms together. 6 times 3 is 18. Now, I know that you're very, very tempted to cross out the 2 and the 18, but remember, we can't do that because there's no value here. When you're dealing with fractions, in order to pull a GCF out, it has to be in every single term. Only being in one term, it's not a GCF of the whole numerator. So this is my final answer. I can't reduce that. All right, next one. I see the square root of 6 over the square root of 3. My denominator is the square root of 3, so I'm going to go ahead and multiply the top and bottom by the square root of 3. The square root of 6 times the square root of 3 is the square root of 18. And then again, for the bottom piece, the square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is 3. Now, the square root of 18 does have a perfect square living inside of it. The square root of 18 is the same as 9 times 2. The square root of 9 is 3 square roots of 2. So in the numerator right here, instead of writing the square root of 18, we're actually going to write its simplified version, 3 square roots of 2 over 3. I have a 3 in the top and the bottom in both terms, so they can cancel, and my answer is just the square root of 2. Now be very careful. Remember we talked about some very common square roots. So remember, this is just kind of a little side note. The square root of 18 will always equal 3 square roots of 2, as well as the square root of 12 always equaling 2 square roots of 3. So these are just kind of some shortcuts to help guide you, easy kind of simplifications, so you don't really have to think about them. The ACT really loves to use very easy square roots to work with because remember, the whole test has to be done without a calculator. So the math and the square roots that they're picking can't be super difficult. Let's try the next one. So we have this big square root of 6 over 10. So to do this problem, if you have a big square root over a fraction, you can pull the square root to the top and you can pull the square root to the bottom. These fractions are equivalent. Now we can rationalize. Multiply by the square root of 10 on the top and the bottom. Remember, we're just changing the fraction's appearance. We're not changing the numerical value. 6 times 10 is 60. And then square root of 10, remember your shortcut, the square root of 10 times the square root of 10 is the square root of 100, which is 10. That's how we get this bottom term. Now the square root of 10 or the square root of 60 can be simplified into the square root of 4 times 15. The square root of 4 is 2 square roots of 15. So as we write our final answer, we're not going to write 60. We're going to write its simplified version, 2 square root of 15 over 10. Then I'm going to go ahead and simplify right here. 2 over 10 is the same as 1 over 5. So if I want to write 1 over 5, I can, and then my square root of 15 sits in the top. Or you can just write square root of 15 over 5. Just be careful, just mind the fraction. One thing I think that is the easiest is breaking down the square root on top of the square root, just so all the math kind of stays together. It's really easy to get lost when it comes to square roots and radicals. So any kind of little tricks you can do to kind of help yourself be organized will help you. Okay. All right, let's try this one. Again, I have a square root in the denominator. That square root is 6. Same idea as before. 5 times the square root of 6 is 5 square roots of 6. Negative 2/3 times square root of 6 is negative 2. And then 3 times 6 is 18. Notice 18, we're going to have to simplify. In the denominator, the 6 comes down. And then you're left with the square root of 6 times the square root of 6, which is the square root of 36. And the square root of 36 is 6. Multiplying those two together, we get 36, which goes on the bottom. I see the square root of 18. I know that that can simplify into the square root of 9 and the square root of 2, but I'm going to go ahead and use this little shortcut, and I'm just going to write 3 square roots of 2. So as we simplify this problem, I get 5 square roots of 6 minus 2 times 3 is 6 square roots of 2 over 36. 5, 6, and 36, they don't have any common factors, so I can't do anything with that, so I'm finished. All right, the next problem is simplifying square roots, okay, simplifying radicals. Anytime you're dealing with radicals, I know a lot of us like to use factor trees, so I'm actually going to do both. Okay, I'm actually going to do both, and let me rewrite the question right here because I want to make sure that all of you are getting the answers that you need answered. So I'm going to do it the shortcut. I'm going to do it the long way using the factor tree, okay? So to start, I'm going to start this one using the factor tree so I have a little bit more space. So let's say that I don't know where to start. I know that this is an even number, so I know that 2 goes into this. Okay, again, this way is a little bit slower, but if you're not sure what to do, this way always works. All right, so I'm going to bring down the 243. I know that 243 is not even, so I'm going to divide it by 3. That's the best way. So then I'm going to get 3 times 81. I can break this down into 9 times 9, which is the same as 3 times 3 and 3 times 3. Now, the way that you pull out the factors, okay, I'm going to leave a square root down here because we will have some things in the square root. You group them in groups of 2 because a square root has an index of 2. That's why we group them in groups of 2. So I have a group of 2 3s, a group of 2 3s, which means they can be free. Okay, those can be free. So I'm going to pull out a 3 and a 3. Like each time you have a group, you pull one of them out. Now, what I'm left with is 2 and 3. Those have no pairs. So 2 times 3 is stuck underneath. Okay, that's how you do these. Now, we're going to think of numbers. So I'm going to think of the x to the 4 as x times x times x times x, and I'm going to group them in groups of 2. 1, 2. I have 2 groups of x, making this x squared. The number of groups becomes the exponent. Then for b, I have 1, 2, 3 groups of b, so this exponent becomes a cubed. For the c value, I have 3 c's, 1, 2, 3. I can only group one of them, so I can pull one c out, and this c is stuck underneath, okay? So let's just kind of rewrite this a little bit more organized. 3 times 3 is 9. X squared b cubed c. Square root 2 times 3 is 6c. So this is the answer. That way took a lot of work. I'm not going to lie. Okay. They take a little bit longer when you're working with the factor tree. If factor trees aren't really your style, you can always do division, which is what I'm going to do on this case. So to do the division, I use these perfect squares. Go ahead and fold my paper real quick. All right, I'm going to use the perfect squares. All I'm going to do is divide. So 486, I'm going to start at 400. And this is going to seem time consuming, but obviously 400 is not going to divide evenly into 486. Okay, all you're going to do is just keep dividing those perfect squares until it works. Okay, so I can continue this trend as long as I need to, as I kind of work through this problem. You know, it's honestly time consuming. Okay, all of this is time consuming unless you know all of those perfect squares. So as you kind of continue this trend, I'm going to keep going. You can skip numbers if you know they don't go into it. For the sake of the example, I'm not, just so you know. Obviously, 100 is not going to go evenly into that. And then I get to 81, and I'm like, all right, 81 goes in 6 times. So I'm just going to break this down. This is 81 times 6. The square root of 81 is 9, and the square root of 6 is left behind. That's all you do. Like, that's it. This square root of 81 is free. The square root of 6 is stuck underneath. That's all you have to do. Now, we did get to that answer. It took us a little longer, but we did get there. Now, in terms of grouping your variables, this is not a bad way to do it. Or you can remember that the index is 2. So the way that I like to do this is I go, okay, how many times does 2 go into 4? Well, 2 goes into 4 twice with a remainder of 0, which means x squared is free and there's no x in here because the remainder is 0. How many times does 2 go into 6? 2 goes into 6 3 times with a remainder of 0, meaning b has a value of 3, exponent of 3 on the outside and none inside. How many times does 2 go into 3? 2 goes into 3 one time with a remainder of 1. So notice we do get the exact same answers here. One is just a little bit quicker than the other. It's completely your preference, but as you get better at this, I hope you pick this method versus writing every single step out. Or if you are writing every step out, I hope that when you get to 81, you recognize that that's a perfect square and you can stop. Okay, this rest of this was unnecessary. All right, let's continue on. So I've got 180 here. I'm going to break up my 180. So factor tree it is. We'll start with the factor tree. So 180 divided by 2 is 90. I'm going to divide 90 by 2 again. I get 45. 45, I'm just going to go ahead and divide by 5. I know 5 goes into it. 3 and 3. Going to look for those groups of 2. So this 3, remember, is just kind of being brought down. It's along for the problem. I'm going to write my square root, and now I'm going to group. I have a group of 3. So I'm going to write a 3. Have a group of 2. So I'm going to go ahead and write a 2. I'm going to leave 5 inside. So remember, this 5's got nowhere to go. So we're done here. Okay. Next, how many times does 2 go into 3? 2 goes into 3 one time with a remainder of 1. How many times does 2 go into 5? 2 goes into 5 2 times with a remainder of 1. How many times does 2 go into 1? Well, that's a decimal, so we know that C is in. Next, we're going to go ahead and combine. 3 times 3 is 9. 9 times 2 is 18. YZ squared, square root of 5YZC. All right, let's try the back. All right, on the back, same idea. Same idea here. So looking at the square root of 10, I'll go ahead and break it down since a lot of us are seeming to like the factor tree method. 55. 55 is 5 times 11. So hopefully we notice that 110 actually can't break up. So 110 is stuck inside. So 110 is stuck inside. These are all individuals, so it can't do anything. We're really just going to focus on the x's here. So index is 2. How many times does 2 go into 2? 1 time with a remainder of 0. How many times does 2 go into 3? 1 time with a remainder of 1. 2 into 1 doesn't go, so that is your answer. Nothing too complicated. We just can't simplify 110. Totally fine. All right, 125. I hope that we can recognize that 25 goes into 125. So when I square root this, the square root of 25 is 5, and the square root of 5 is going to be stuck inside. Let's start pulling our stuff out. Index is 2. How many times does 2 go into 10? It goes into 10 5 times. 2 into 6, 3 times. 2 into 3, 1 time with a remainder of 1. 2 into 2, 1 time. I hope this is getting a little bit easier understanding how to get the exponents with division. Next, we have the conjugates. Now, we know that these are conjugates because we have pluses in the denominator with our square roots. So when you do conjugates, you only manipulate the middle sign, not the sign in the front. So if this was -3, it would stay a -3. So I have 3 minus the square root of 2, 3 minus the square root of 2. Again, our goal is perfect or a difference of squares. Let's go ahead and do the top first. 5 times 3 is 15. 5 times negative square root of 2 is -5 square roots of 2. In the denominator, I do 3 times 3, which is 9. And then I do the square root of 2 times the square root of 2, which is the square root of 4. And the square root of 4 is 2. Remember, that's how we're getting those values. It's always subtract in the center. So I get 15 minus 5 square roots of 2. 9 minus 2 is 7. There is no GCF that goes into 7, 15, or 5. So I'm stopping here. All right, number 18. Same idea. 2 square roots of 3 minus the square root of 2. 2 square root of 3 minus the square root of 2. I'm going to distribute 3 square root of 5 times 2 square root of 3. I'm going to multiply the 3 and the 2 first. So 3 times 2 is 6. Square root of 5 times square root of 3 is the square root of 15. 3 square roots of 5 times negative square root of 2 is just -3 square roots of 10. To do the denominator, this one is a little harder. I get 2 square roots of 3 squared, basically. So I get 2 squared times 3 square root of 3 squared. 2 squared is 4 times 3, which is 12. So my first value is 12. Square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. Always subtract. Can't simplify anything at the top, so I'm just going to keep it. 12 minus 2 is 10. There is no GCF between 6, 3, and 10, so you stop here. All right, next problem. 19. I'm going to multiply top and bottom by 9 minus the square root of 5. This one takes a little bit more distributing. So I have 9 times 6, or 6 times 9, which is 54. 6 times negative square root of 5 is negative 6 square root of 5. Now, we have to make sure that we distribute everything. So I'm going to do negative square root of 2 times 9 is negative 9 square roots of 2. Negative square root of 2 times negative square root of 5 is positive square root of 10. Hopefully we notice looking at the top, I can't do anything with that, so I'm going to leave it. 9 times 9 is 81. Square root of 5 times the square root of 5 is the square root of 25, which is 5. And I'm going to kind of do a little shortcut right here. I know that I'm going to subtract them. So 81 minus 5 is 76. And I'm just going to go ahead and write this 76 here. There is no common factor between 54, 6, 9, or 76 that will go into all those evenly, so I stop here. All right, next one. I'm going to do 6 minus square root 6 on top and bottom, and I'm going to distribute. Square root of 2 times 6, 6 square roots of 2. Square root of 2 times the negative square root of 2, or 6 is negative square root of 18. I hope we recognize that that can simplify. Continuing on with the trend, 6 times 6 is 36. Square root of 6 times the square root of 6 is the square root of 36, which is 6. Again, these can subtract. 36 minus 6 is 30. We need to make sure that we're simplifying square root of 18. Hopefully we remember that the simplified version of the square root of 18 is 3 square roots of 2. Okay. Oh my goodness. Oh, I'm totally messed up because that's not right. I'm sorry. All right, let's kind of go from here. This should be the square root of 12. My bad. I'm sorry about that. 2 times 6 is 12. I'm sorry. And then I can simplify that into 2 square roots of 3. Sorry. It's late in the day. It's after school. I'm filming these. So my bad. It's okay. So now I have 6 square roots of 2 minus 2 square roots of 3 over 30. Hopefully I can see a GCF here. My GCF in this case is 2. So I'm just going to kind of make a note to myself that the GCF is 2. So I'm going to pull a 2 out of everything. 6 divided by 2 is 3. 2 divided by 2 is 1, so negative square root of 3. 30 divided by 2 is 15. So I pulled a GCF of 2. All right, 21. I'm going to multiply the top and bottom by 10 minus square root 2. 10 minus square root 2. 6 square root of 3 times 10 is 60 square root of 3. Square root of 3, 6 square root of 3 times square root of negative square root of 2 is negative 6 square root of 6. Simplifying underneath here, 10 times 10 is 100. Square root of 2 times square root of 2 is the square root of 4. The square root of 4 is 2. We subtract to get 98, which goes on the bottom. Hopefully we can recognize that all of those are even. So my GCF in this case is 2. So when I pull a 2 out of the numerator, 60 divided by 2 is 30. Negative 6 divided by 2 is negative 3. And then 98 divided by 2 is 49. Okay. From here, there's nothing else that can simplify into 49, so you're finished. All right, very last one takes a little bit more math, nothing you can't do. So 6 square root of 6 minus square root of 11. Lots of distributing, it's okay. 2 times 6 is 12, not 18 like I wrote above. Square root of 5 times square root of 6 is the square root of 30. Square root of 30 can't be simplified. Shifting over here, 2 times the negative 1 is the negative 2. 5 times 11 is 55, so square root of 55. Hopping over to my negative 7. Negative 1 times 6 is negative 6. 7 times 6 is 42. So I have negative 6 square roots of 42. Again, negative times a negative is going to be a positive 7 times 11 is 77. Let's extend that line out. So right here, again, a little bit more math. 6 times 6 is 36. Square root of 6 times the square root of 6 is the square root of 36, which is 6. Okay, so 36 times 6 is 216. Same pattern, square root of 11 times square root of 11 is the square root of 121, which is 11. I'm going to be subtracting those, so I get 205, which goes in the bottom. Those values have no like terms. You cannot simplify any square roots, so this is your final answer.